Welcome everyone to this week's SMaRT seminar series, which is jointly organized by IIT Delhi and John Hopkins University. So today we are pleased to have Dr. Subhayan De. He's an assistant professor at the Department of Mechanical Engineering at the Northern Arizona University. There he heads the Euclid Lab, which is pronounced as Euclid, but it's actually UQLID, where his group develops probabilistic data-driven frameworks using machine learning to efficiently model and design multiscale and multifunctional systems under uncertainty. He has earned his PhD in civil engineering and has also earned an MS degree in electrical engineering from University of Southern California. The topic of today's talk is multi-fidelity machine learning for uncertainty quantification. Dr. De, thank you so much for taking out the time to give this talk. We really value your time, and the virtual floor is now yours. Thank you so much.
Yeah, thank you, Razi, for the kind introduction. So, as Professor Naik was mentioning, I had the Euclid lab, but if you look at the letters, it starts with UQ. So that is for uncertainty quantification, and that is going to be the focus of today's talk. And we will try to address uncertainty through some multi-fidelity machine learning methods. So this will be the outline of my talk. So I will mainly focus on three topics: how you can do multi-fidelity aspects during the training, and also like the architecture of your neural network, and then finally I'm going to talk about how you can even manipulate your problem formulation to introduce the multi-fidelity aspects while trying to model systems where you have uncertainty using machine learning techniques. So let's start with our motivation and discuss why we should talk about uncertainty and why does it even matter. Now, I like to start with this quote from Albert Einstein, which essentially says, as far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. So what does this mean? So that means we cannot essentially, with certainty, say the mathematics that we are using to represent some system, the model we are using to describe an engineering system, that might not be true or certain within the application that we are doing. So the presence of this uncertainty is ubiquitous. Now, if you look into how these different sources of uncertainty comes into modeling, you can ask yourself these questions. Do the equations model the physics exactly? How accurate are your model parameters? Even do you know the initial or boundary conditions that you are using, they are precisely known? And I can go on. But what you should get from this slide is that what happens with the modeling of your engineering systems is that there are so many sources of uncertainty, so that your quantity of interest, the output that you get from your model, will also be uncertain. So that is something to be mindful of. So now let's talk about what are the effects of this uncertainty. Now, if they are not properly addressed during modeling, planning, or design phase, the result can be disastrous. So I have on the left-hand side an image from this Challenger disaster, which happened during the launch of this spacecraft, and there were astronauts inside the space shuttle who unfortunately lost their lives. Now, you can actually see some of the live coverage of this unfortunate incident on YouTube. So after this incident, they did some inquiry. So what came out of that inquiry is that one ceramic ring in the booster rocket, known as the O-ring, which is there to seal the booster rocket, failed. Now, the probability of failure when they designed was for temperature of 60 degrees Fahrenheit, and that probability of failure was only 2%. But when they launched, the temperature outside ambient temperature was 31 degrees Fahrenheit, and that probability of failure increased to 13%. And this happened. So if they would have put more emphasis on understanding this, the effect of this uncertainty, this effect of this probability of failure, they would have prevented this. Now on the right-hand side, we have this image from an earthquake damage. As you know, during the design phase, you need to incorporate design changes based on what would happen if you have a certain magnitude earthquake. Otherwise, this kind of thing will happen. Now, the issue is incorporating uncertainty in our analysis is not going to be easy. It's going to be it's going to cost you significant amount in terms of computational cost. However, we must address this if we want to perform some robust modeling and simulation. Now, this is where the neural network surrogates comes in. So what we are going to try to do with our neural network surrogate is that we are going to try to replace this model part, generally, which is expressed as partial differential equations that describe the system. But again, as I said, the mathematics might not with certainty express the real system, but so there will be uncertainty. So in the whole relation, there are uncertainty in it, but we are still going to try to model it with neural network and between this input x and the quantity of interest. And this is happening because of the recent advances in the computing power, as you know, so that we can train large networks to essentially learn these relationships. Now, how do this neural network help us? Now, they have high degree of expressiveness. There are abundance of software tools that you can use. And also the training is very easy with low order optimization schemes. However, you need to have a large amount of training data and you have a lots of parameters to tune. So these are the two challenges that I will try to address in today's topic, through today's topics. Now, in terms of architecture, you have a lot of options. For example, on the right, you see a feed-forward neural network. There can be residual neural network and so on. I will not get into the details of that, but there are quite a few options. If you are interested, you can look into it. Now, the next part of this presentation is that by using bifidelity models. Now, we talked about that neural network requires a lot of training data. How do I get a training data from for a physical system? So we can either do a large experiments, but that is going to be difficult in many cases, or we can simulate very accurate models, which are known as high fidelity models, but at the same time, they will require more computational resources. So unfortunately, we cannot generate large data sets using these high fidelity models. However, we also often have access to low fidelity models, which require small computational budget, but generally their accuracies are low. But the good thing is I can generate a large data set, training data set that I can use initially, and then we will see how we can use a small amount of high fidelity data to retrain and modify my network. So this is the essential question that we are going to try to answer in today's talk. Can we efficiently train neural networks using a small data set from the high fidelity model, but a large data set from the low fidelity to perform efficient uncertainty quantification? So uncertainty will be there in all the examples that I'm going to show you today. Now, we are going to look into three perspectives: how we can modify our neural network training, how we can modify our neural network architecture, and then the final one is interesting. We are going to try to even work with the problem formulation itself to modify it and use our neural network in an intelligent fashion. Now, before I get into each of these, I want to mention that you can, of course, improve your sampling techniques, but we are not going to get into that. So there can be other. I can increase the bullet points here, but we are going to focus on these three aspects today. Now let's start with changing in the training paradigm. So we are gonna go through these two topics, transfer learning and L1 regularization. So transfer learning uses the knowledge gained from solving one problem to solve another related problem, especially where you do not have accurate or labeled data, or even if you have, they are limited. Now we can use the similar concept here where we will start with our training with low fidelity, and then we will move on to using the knowledge gained from the low fidelity training and move on to high fidelity data set, which is unfortunately scarce. Now, what are the advantages of this? First of all, since you have already gained some knowledge from a related low fidelity model, they might not be full quite accurate, but they will still give you some information that can be used to train the neural network enough to learn some of the basics of the problem. So that's why you start with a small initial training error, and then you can also have a faster convergence of the optimization scheme. And then you generally get similar or even sometimes smaller validation error using smaller data sets. Now, as I have shown here on the right side figure, so this is where you have the transfer learning advantage. So as you can see, the red curve lies well below the blue curve. But as you add more and more high fidelity data set, high fidelity data points to your training data set, generally the advantage diminishes and there might be a crossover point itself. So when you are in the regime of having a very small high fidelity data set, this transfer learning is advantageous. Now we looked into quite a few options to do this transfer learning using low fidelity and high fidelity data set, but this particular approach was really helpful. So I'm going to discuss this today. And if you want a comparison with other approaches of transfer learning, please go through this paper at the bottom of the slide. Now, in this one, by fidelity weighted learning, we used a two-stage training procedure. We have a student and a teacher. Now, the student is the neural network itself, which we ultimately want to use as our surrogates, and then we have the teacher, which will be trained using high fidelity data set. And this teacher, for this teacher, we have quite a few options, but we are going to use a Gaussian process. Now, once we train the GP with our high fidelity data, we try to predict everywhere using like at the location of the low fidelity data itself. And then we form this soft data set, which essentially has the uncertainty information that we will use in the green box here during training. As you can see, the uncertainty information is right there to basically inform how I will change my step size or learning rate parameter during retraining of the student network. So student network, we initially train with low fidelity data, and then using this soft data set, I'm going to retrain. So this training, this retraining part in the green box is important because it uses the uncertainty information. Now, we use this in modeling of a lithium-ion battery, where we have 17 uncertain parameters for the properties of anode, cathode, and separator. Now here, the low fidelity model is actually 7 times faster. And for the bi-fidelity training, we used only 20 high fidelity data points, whereas 140 low fidelity data points. Now, if you look into the neural network architecture, we just use 2 hidden layers with 50 neurons each. And when we compare the two architectures, the feed-forward neural network and the residual network, and then using this training paradigm by fidelity weighted learning, as you can see, we are in the table, we actually have reduced the mean validation error by almost an order of magnitude. Now, let's do one more example of this. So we did flow around this NACA airfoil, And our quantity of interest is the coefficient of pressure at the surface of the airfoil with 4 parameters as uncertain. Now, here the low fidelity model has only 9,000 elements, so it's not very accurate, whereas the high fidelity model shown on the left has 241,000 elements. So if we compare the computational cost of each of these models, the low fidelity model is almost 500 times cheaper to evaluate. So generating data from the low fidelity model is much easier. Now, here the neural network is 4 hidden layers, 50 neurons each, so nothing more complicated. And let's see what happens with our results. As you can see, again, we gained almost an order of magnitude accuracy by using this bi-fidelity weighted learning. So the next topic that I'm going to discuss in the training is the regularization. Now, before I do that, let's talk about some pruning of neural networks, which is quite common in the literature. Now, as you know, the deep neural networks that you are using often have multiple hidden layers with many parameters. So they are prone to overfitting, especially when you train using small data sets. So what people are doing is they are looking into these large neural networks and started to pruning them to obtain pruning some of these connections to obtain sparsity in the networks and its parameters. Now here there's a lottery ticket hypothesis which came out in 2018, which essentially states that if you start with a dense network and randomly initialized dense network, then actually there exists a pruned version of it, so pruned subnetwork, which is known as a winning ticket, which has a similar performance. But the issue here is um, there's no recipe given to find that winning ticket. So let's see if we can find that winning ticket, which will essentially give me a much smaller network that will have the same performance as the dense network. Now, how we can do that? We can, of course, use a hard threshold on the sensitivity of the training error with respect to any connection, and then just simply delete that connection in the network. Or we can augment the training objective by including regularization and then suppress those connections. So we are going to use this second approach using regularization. Now, just to give you some background, so you use on regularization, which you used as an addition to the objective of the optimization to prevent overfitting. And the most common one is the standard L2 Tikhonov regularization, where the regularization term essentially defines the surface of a hypersphere. Yeah, and then if we really want to go for sparsity in the parameters, then we can use some L1 regularization. Now, unfortunately, in the standard L1 regularization, you can also find a non-sparse solution too. But if you really want to focus on the sparse solution, you can do a weighted version of it, and that is something we are going to use also. So essentially you have a weight matrix multiplied by theta inside your L1 norm. Now, with this background, let's see how we can use this regularization strategies to train our neural network. Now, to compare with only high fidelity only version, so we are going to use the standard L1 and the weighted L1. So standard L1, as you can see, we are essentially using L1 norm of the network parameters. Now for the weighted L1, the weights, what we are going to do is during training, we are going to take the weight from the previous iteration and then do an inverse of that in our diagonal of that weight matrix W. Now we also have to add some small number to avoid divisions by 0. Now here comes the bi-fidelity part. So for the standard L1 regularization, but with bi-fidelity training dataset, what we are doing here, the modification that in the training is that we look into how the parameters are different compared to your low fidelity train version. So the difference goes right into calculating the L1 norm, and that's we are going to say the standard L1 regularization, but with bifidelity. Now, for the weighted one, instead of using parameters from the previous iteration during training, we are use the low fidelity parameters and take the inverse of it and put it into the diagonals of our weight matrix. Now, if you want to take a look into more and discussion related to it, please go through this paper, which is listed at the bottom. There we have also proved some bounds for the generalization error and showed how this kind of bifidelity strategies, training strategies can help. Now, here I just want to make a few points before I move on to showing some examples. So the transfer learning uses the knowledge gained from solving one problem to solve another related problem, right? If you recall, that's what we mentioned a few slides ago. Now, how does this regularization strategies fit into that? Now, if you think of it, it can be thought of as a generalization of transfer learning, this regularization strategies, but instead of you completely freezing some of the layers, which you do in standard transfer learning, um, here you use regularization to induce small variations in the high fidelity trained network. You are still gonna, instead of completely freezing, you are still gonna allow some changes, but still you would like to induce only small variations. Now, um, if you want to read more about it and a full discussions related to it, the paper has that discussion. But just to keep in mind, there's a connection with transfer learning. So these training strategies, these two, the initial one with transfer learning and with regularization, they are related. So with that point made, let's move on to an example. Now we are going to take a look at this thermally driven flow in a cavity. Now, on the right hand side, you have a cold wall where the temperature of the cold wall is written using a 50-term Carhon and Loeb expansion with exponential correlation. And on the left side, you have the hot wall. And in addition to that, you have the temperature of the hot wall and the kinematic viscosity as uncertain. So in total, you have the 50 term coming from the KL expansion and the two more. So you have 52 uncertain parameters. Now in terms of the data set, we took 150 data points from the low fidelity model, which is essentially a 16 by 16 mesh, which is very coarse. Now for the high fidelity data set, we took only five from 256 by 256 mesh. For the neural network, we used 4 hidden layers with 52, 60, 60, and 25 neurons each. Now let's take a look at the effect of all these regularizations. So remember, we can always compare to a case where I do not use any regularization with high fidelity dataset, and then we can do a standard L1 and weighted L1 with high fidelity that I showed. Now that showed in the top row. Now in the bottom row, the bifidelity standard and the bifidelity weighted L1 are shown. So as you can clearly see, the histograms are shifted a little bit to the left. Now, if you especially look at the table, you can see the order of magnitude has decreased when you compare the mean validation error. So we again obtained one order of magnitude improvement in the validation error. So with this, I'm gonna one more slide here. So yeah, we said we are gonna prune the network, right? So we are going to make most of the parameters as very small, and only a few of them will have significant values. So, so those connections are important connections. Now, if we look at this plot, I know there are a lot of histograms there, but let's just see how we can interpret this. So if you go row wise, so it just compares different regularization strategies. If you go column wise, it compares different layers weights parameters. Now I want you to focus just to this yellow histogram in the middle column. So I have highlighted with red. So see, only a few parameters have significant values because most of the Euler histograms are 10 to the has values are for values 10 to the minus 5 or even less than that. So if you focus on this red highlighted portion, and you can see only a few of the network parameters have significant values. So we have indeed pruned our network with this by fidelity, weighted by fidelity L1 regularization. Okay, so then let's go to the next aspect of this talk, which is the multi-fidelity architecture. So DeepNet architecture originally proposed by Lulu et al. In 2019, which um, are essentially mesh-free operators built with neural networks and have the ability to transfer solution between meshes. And also you do not need to know the underlying governing equations. Now, this architecture we are going to use. So I am just giving you an overview of it. And what it essentially does is you have a trunk and a branch network, and then you get the coefficients and corresponding basis functions from out of these two, and then you can do this expansion shown here at the bottom. So you get the approximation of your solution operator itself. Okay, so we are going to use this, but we are going to make a bifidelity version of it. Now, how do we do that? So we are going to take the response and divide it into two parts, a low fidelity part and a discrepancy part. Now, we will use the DeepNet architecture to estimate this discrepancy. And our assumption is training a DeepNet for this discrepancy is much easier instead of training a DeepNet for the whole response. So for the low fidelity solution, we can easily we will easily get it from a simpler model or computationally cheap model. But for the UC, the discrepancy part, the correction part, we are going to use a DeepNet. Now, again, you can look into this paper at the bottom for more details. Now, we are going to use it for parametric uncertainty, where basically you have, let's say you have a system where your governing equation has some deterministic part and some stochastic part. So we can just pick the deterministic part and write down our low fidelity model. And then what we are going to do, this is important. So we are going to take the output of this low fidelity model and use as the input of our branch network. Now, with this, we can write down we can write down our full response as your low fidelity response plus this expansion that we get from the DeepNet approximation. Now, we can also use this for structural uncertainty, where you essentially have a system described by some known part of the governing equation, as well as there's some unknown part, but unfortunately you don't know that. So what you can do in that case is write down your low fidelity model with the known part, and then use your DeepNet architecture to assume to approximate the correction part of your response. Again, remember, you need to use your low fidelity response as input to the branch network. Now, the expression for the whole response is shown below. It's similar to before. Now let's see how we can do this. So for a real example, so we took out this example of a wind farm layout. You want to place these 6 wind turbines, and what your quantity of interest is power generated, which is very important for a wind farm like this. Now, as you can guess, your wind speed, wind direction, and yaw angle, which is basically the angle the wind direction makes with your turbine axis, it's going to vary. So these are going to be my uncertain parameters. Now for the measurement data, we took real measurement data from Princess Amalia wind farm in Netherlands, and your joint probability density function for wind speed and wind direction shown at the bottom. Now, we use the wind AC package, which comes out from the National Renewable Energy Lab that you can use to perform wind farm simulations. Now, for our 2D for our low fidelity model, we used a 2D version of it. And for the high fidelity model, we used a 3D version of it. And as you can guess, running the high fidelity version is much more costly. Now, that's why we only used 100 high fidelity data points for training, but um, and we kept aside 1,000 for validation, but we used much more for our low fidelity during the training. Now, the bottom two histograms shows how we essentially move the validation error towards left. So we make them very small as we use this bifidelity scheme. Now, this is also shown in the table on the right. We actually reduce the order of magnitude of the validation error. All right. So that was helpful. Now, yeah, we already discussed how you can modify your training, how you can modify your architecture. Now let's talk about the problem formulation itself. So for this, we are particularly focused on locally nonlinear systems. Now, in engineering, you often do encounter those. For example, if you are looking at a building, the superstructures are generally considered linear, whereas if you go to some isolation layer or in the example that I will show, I have some tuned mass dampers, those often behave nonlinearly. So, but the good thing is those nonlinearities are localized, right? Uh, so what can you do? You can do linearization, or you can do nonlinear solver to solve the uh, governing equation of the whole system, but they will incur increased computational cost, and that you are trying to avoid. So again, I can always use some intelligent sampling techniques, but that's not the focus of this talk. So what we are going to try to do is exploit the localized nature of these nonlinear components. Now, to do that, we need to go and take a look at the state space equation of the nonlinear system. So if we write down that state space equation, what we are essentially going to do is write the nonlinear part as this L, which is the influence matrix for the nonlinear function G, and then write down G as a function of X bar, where X bar is essentially a subset of your full state. Now, this is what the nonlinear system that we are going to utilize. Now, here I have my uncertain parameters as before. So now let's take a look. So this is very similar to what we just used before when we were talking about bifidelity deponent. So we are going to write down this response composing of a low fidelity one plus a correction term or discrepancy term. That term is going to take care of the effects of nonlinearity as well as any uncertainty that you have in the system. So if we go and remove that term, so we will essentially get our nominal linear system, which is the low fidelity system. Now, solving this is going to be just a one-time cost. So we can solve this nominal linear system. And then if we want to write our response, we can use the impulse response function, and we can write the top two equations, which gives you the response and the output y. Now, there's still some issues. Previously, we used deponent to approximate that correction term, the discrepancy term. But if you really want to do it analytically, it's really challenging, as it implicitly depends on your state X bar, which includes both the linear part and the correction part. So it's an chicken and egg problem, and there's no other way than to use a iterative approach. Um, and I will show how we can do that. But so at this point, we had to do something, and what we essentially did is introducing this pseudo force term. So if you think of this effect of this nonlinear function g as a pseudo force, we can write this correction term using this convolution integral with the impulse response related to the influence matrix of the g function and L. Now, once I solve this, I can clearly write the whole response and the output. And if we want to solve these convolutions, you can use FFT to efficiently perform that. Now, here's the thing. So if we directly want to solve this analytically for this pseudo force function, which you can then use in your convolution integral to solve for the correction part, you have to solve this equation, which is a nonlinear Volterra integral equation of the second kind. And that's not easy to solve. You have to use an iterative strategy due to the nonlinearity. Now, instead of using that iterative strategy, we are going to use neural networks to estimate that pseudo force P. Now, the details are in this paper. If you if you want to take a look, but let's go to an example. So here I have a 20-story moment resisting building with 1623 degrees of freedom, and we have 3 nonlinear tuned mass dampers attached to its roof. Now we use a wind excitation, and for the damping forces in the 3 TMDs, we assume a power law model where I have uncertainty in the parameters, 3 parameters right there. Now, for the neural network, we used 4 hidden layers with 200 neurons each. And for the training data set, we use 250 random samples of the uncertain parameter. That's how we generate our training data set. But if you look into the right side figure, top right, our approximation of pseudo force, so which is essentially in this case the force that is going to come out of this TMD in x direction, they are quite a match. Now, if we want to do some uncertain quantification, like what we did at the bottom, you can see how we can plot the mean response and then plus minus sigma or plus minus up to sigma, etc. Now, when we look into the true solution of the mean response, the relative error is in the order of 10 to the power minus 4. Now, how did we get the true response? We actually solved the Volterra integral equation. So that is how even you can manipulate the problem formulation itself to help you to train your network and then get an efficient uncertainty quantification. So it's not just limited to your training algorithm or how you can modify the architecture, etc. Even if you look into your problem formulation, that may help you to find this multi-fidelity aspect. So that's something I want to emphasize today. So and one of the reason I'm emphasizing this, because that is not something that people talk about a lot. They generally, whenever they introduce multi-fidelity or bifidelity approaches, they talk about how they are changing the training, how they are changing the architecture. They do not get into the final topic. So we started with a quote from Albert Einstein. So, but on a lighter note, I'm gonna finish with this quote, and from The Hitchhiker's Guide to the Galaxy, that we demand rigidly defined areas of doubt and uncertainty. Now, let's think about this little bit. So we are not saying we will remove uncertainty anywhere. We are saying we will have uncertainty, but we want to quantify it. We want to rigidly define where our uncertainty is going to affect. So that's what we want. And that's why I really like this quote. And yeah, and another conclusion that we can make is 42 is not the answer of today's talk. That's a reference to this book. I really like this book. Um, so we can say that for large-scale engineering and scientific applications, one of the main obstacles is training neural networks to generate large data sets so that you do not really get into overfitting regime that performs poorly when you go to the validation or test data set. So that's an issue. Now we tried to overcome it by introducing bi-fidelity uh, training, bi-fidelity architecture, and also finally some even modifying the formulation itself. And that really is going to help you to do some efficient uncertainty quantification. So that's the end of my talk, and these are the references that I used. So feel free to get more details by looking into any of it. Thank you for your attention. If you have any questions, let me know.
Thanks a lot, Dr. Shubhande, for the very nice talk and very nice examples that you showed, and how you use uncertainty quantification along with machine learning to actually do these examples. So I would ask the audience if anyone has any question, feel free to ask. Yes, yes, Deepakar Rashakar, please unmute yourself and you can ask the question.
Hi, am I audible?
Yes,
Yeah.
you're audible.
Oh, thank you so much for the wonderful talk, Professor Day. My question is regarding the problem statements that you frame. Like, I'm working with Professor Goswami on a multi-fidelity problem, uh, where our low fidelity comes from the continuum simulation. Let's assume it is the best accurate simulation that we can do, and the high fidelity comes from experiment. Uh, And do you have like how do you recommend validating that the features that we learn from the simulation data can be relevant or can be effectively transferred to the experimental predictions that we are getting? Because there is an inherent difference between our computation model and the real world measurements that we are collecting. Uh, so can you please give a recommendation on how we can
Yeah, I
relate
think
that?
I think you are really getting into this structural uncertainty part. So essentially, you have some unknown mechanics going on that is not captured through your simulation, right? In reality. So you can of course improve your simulation model itself um, to make it more and more accurate. But that doesn't make sense if the computational cost of simulating those also increases, right? So that's why you would like to use this kind of machine learning technique. So I think you should think this problem as like this. You have structural uncertainty. You don't know some of the physics itself. I think that's how you should approach this problem. Now, it's gonna be like I'm dependent on what kind, how your data looks like, and what kind of data you have. Before I can give you any recommendation in terms of the architecture you use, but I'm just giving you an overview, like what approach you should take. Like yeah, I may suggest to you read some papers or articles on how to tackle this uncertainty where you don't even know your model is complete, right? So that's the issue here. And if you're working with experimental data, like you are, I'm guessing you are using some measurements like DIC or something, right? Yeah. So
Uh,
anyway, mm, so
like, I'm sorry, yeah, please
no,
continue.
no, go ahead, go ahead. Yeah.
Yeah, so uh, right now we have a like our challenge is multi-scaling. So it's a multi-scale problem. So we have like atomic scale simulations, but we have a continuum level of experiments. So like there is like we are not able to understand how to bridge the gap between these two.
Mhm.
Uh, so that's where we are struggling.
Yeah, yeah. I mean, you just made the problem more complicated as you gave more details. So
Yeah.
yeah, that is even more challenging, even just handling experimental data when you have some physics model. So yeah, there are some ways to do even use machine learning for um, homogenization and those things that you may want to take a look at. But yeah, essentially, I mean, right now, my suggestion would be to take a look into some of this structural uncertainty part, especially if you find some journal papers, how to handle that. And people were talking about it even before the introduction of machine learning to handle this. So I think you will get some insight into it, but your problem is quite difficult as I understand it.
Okay. Yeah. Thank you so much for
I
this. I
hope
will.
that helps. Yeah.
Yeah. I will definitely look into the structural uncertainty. Yeah. Thank you.
Thanks, Diwakar. I had a curious just add on to that Dibakar's question is that in the case of molecular dynamics simulation, where we are actually starting at a very low scale like molecular dynamics, and we're trying to have some kind of an macro scale experiment like a tension test or something of that sort. Uh, for I think that at at that molecular dynamics level, I think you also need to choose the potential function, and I think the right choice of potential function sometimes can also be a cause of uncertainty. I mean, if you are probably choosing, I mean, I believe I have not worked with molecular dynamics, but I believe that the right choice of the potential function, and I find, I mean, from the few things that I have observed is that people use some kind of a chosen and given in literature kind of potential function, but maybe tuning those potential functions and having uncertainty in the potential functions can finally lead to a lot of changes at the macro scale, because I mean that is just one aspect that you could also think about where the structural uncertainty might come in. I don't know, I just guess. I have not worked with molecular dynamics as much. Yeah. So yeah, so
Yeah.
yes, go ahead. Diwakar,
No,
you could
I was
say.
just trying to say, yeah, I think thank you. Like, I think I can look into this direction. Like, yeah, that is a very good input. Yeah, thank you so much.
Thanks. Any other question for Dr. Day?
Rajdeep, I can go ahead.
Yes,
I
yes,
have a few
please, please
questions.
go ahead.
Yeah, see. Yeah, hi again. So, okay, I have two, three quick questions actually. So the first part you presented, right, where there was uncertainty from the GP, I think, and you were using that to update the neural network.
Yes.
So that was a bi-fidelity approach, if I'm not wrong, correct?
Yeah.
Yeah, this one. I
I mean,
mean,
essentially, what I showed today, all of them are bifidelity, but you can easily extend it to multiple fidelities when you have multiple layers of data. For example, let's say you have two more fidelities of data here in this case, right?
hmm,
So what you will essentially do is you are gonna uh, train more teachers. So one, the highest fidelity, then the another teacher for the next highest fidelity, and you are gonna do this retraining part again and again for depending on how many fidelities you have. Yeah, sorry. Uh,
yeah, no, that was the actual question. So, so what I was asking is that, so in that case, you will have three teachers and one student, or it will be hierarchy where one teacher will become student and it will again act as a teacher. If I look at, let's say, the middle one, for example.
Yeah, you can do two approaches. So as I
Hmm.
was mentioning that, for example, for teacher, you do not necessarily have to use GP. You can also use another network
Yeah,
to
definitely.
to do that, but it's another but a smaller network because you do not have
Hmm.
large
Hmm.
data set. So
Hmm.
so if you want to do that, like instead of training this network with another highest fidelity level of data, so you can do that kind of approach with multiple networks. But if you want to keep focused on just using the neural network just for the student and rather other
Hmm.
teachers, other different fidelity teachers as GP, you can also use that. So it is open to the all these options. So I mean, my personal suggestion is like if you really do not have enough data, I mean, the data that we handle is, I think, 10, 20 for the high fidelity. We stuck to GP and to basically inform the neural network retraining. But you can either directly retrain, like you can do like an approach where you go from the bottom. So you just train with a little bit better teacher, and then again check that student network and do one more iteration like this. Or you can come from the top where you basically inform the highest level data to inform your best teacher, and then ask that best teacher to modify the next network that you trained with a little bit lower fidelity of data, and you can go to bottom. So you can do a lot of things. So this is just to give you some guidance on how you can do this teacher-student model. And to be honest, teacher-student model was there even before neural network and all these things. So this kind of approach, and this is very interesting. It is related to our daily lives, if I can say.
Yeah. No, this is interesting because you are using the uncertainty, right, to inform your update. And that is, I think, the most interesting part, at least to me. And this uncertainty, I guess, is the predictive uncertainty, right? That sigma xb, that's a predictive uncertainty, right?
Yes.
And that you are using to, so that means your update. Now, this predictive uncertainty is a function of the locus x, right? The input.
Yes.
So that means your update is also function of input, or in some sense.
Yeah, so that's how we form the SOP data set. So when you have for the high fidelity data set, you have all these points where you see this. But for the low fidelity, if your teacher is confident enough, it will predict low uncertainty. But if the teacher is not confident because of the sparsity in the high fidelity data set, so you will essentially have predict, oh, I'm not that confident. So you will allow allow your network to learn accordingly. So that's how it depends where your low fidelity data points are as well, because you are combining both of them in the soft data set. But it's going to depend on the how confident the teacher is in those locations. Yes. Yeah.
Right. So yeah, this question I'll ask later. The other one is the straightforward one, right? So you use L1 and the results were really encouraging. But there is a series of work, right? Specifically from Cornell and Nicholas Boklas's group, where they're working on L0, which gives even a tighter network, like you get expression out of it if you really push it to the limit. So did you try that, or what is your opinion?
So with the L0, if I know correctly, so there's with L0, the issue is with the calculating the derivatives. So so I think this issue of sparsity was also addressed by the group from Professor Kutz, Nathan Kutz, and that group, like why L1 might be better. And even they used I didn't come up with the weighted L1. It was already there, right? So I used a bifidelity version of the weighted L1 and saw this is working. So there are a lot of works in terms of regularization. Now, where our work stands out is proposing these two strategies where we are essentially using the bifidelity version of it, and also we provided a proof of like your generalization will indeed be bounded, and that bound is tighter for bifidelity version. So that is what our work is there. And currently, to be honest, I don't recall if I have cited the papers that you mentioned, but I think
they are more recent. I think the L0 ones are more recent from Cornell, Nicholas Boklas's group. So they actually are pushing that idea quite a bit on different type of networks, mostly on the intersection of materials or constitutive relation plus AI, that kind of domain. But I found it to be interesting. Maybe I think it may be interesting to you as well. But seemingly those are quite recent, I would say.
Okay. No, that is a good point. And if you could use L0, that will give you a much better, much better sparsity. And that's what you ideally want to use.
Exactly. So they were looking at this to find out expression that you can use, because it will be a complex expression. You cannot probably make much sense out of it. exponential inside sine or something like that. But
Okay.
nonetheless, expression you get out of it because it compresses it so much because of the L naught thing.
Okay.
So, but
I
yeah, I
guess-
mean, obviously, it's an open
I guess
question.
that using L naught is as tantamount to dropping those networks. I mean, dropping those
Many
connections.
of those, right? It will go to zero.
Yeah, many of those. Yeah, right.
Yeah.
Yeah.
And last, yeah, go ahead. Sorry.
No, I just wanted to mention that that's what you want to do while you're pruning, right? And you are trying to find this winning ticket. That's your goal.
Mm.
Yeah. No, but that is interesting. So
Yeah.
I definitely take a look at this recent work with L naught. But one of the reasons that we didn't do with L naught is with the
Differentiability.
calculating, derivatives of it. Yeah.
Lastly,
Thank
and
you
this
for
is
that.
more of a philosophical question. Not a philosophical question, but maybe an open question also. So when we do multiplicativity, right, we generally assume that it's probably a solver and experiment, and we know a priori that this is my low fidelity and this is my high fidelity. And my formulation builds around that. That low fidelity and the discrepancy will be learned by the higher fidelity model and so on and so forth. But now if I take this problem, and maybe we have some historical data measured by different sensors, but we don't know the sensors any longer. So that means I have data of multiple fidelity, but I don't know which data is of which fidelity. I mean, is there some way to find that and then bring that into the picture? Because you have worked extensively in this area. So I thought you might have some idea.
Yeah, unfortunately, I didn't work in that area, but I think what you are getting at is how to rank the fidelities.
Yeah, exactly.
This is even a problem, you have multiple models and you don't know how to rank them, right? So, and the data is coming from multiple models, not even like how the sensor are placed or etc. So it's a more general problem. Now, traditionally I relied on experts opinion on okay, this is my fidelity, this is my low fidelity. Now it's easy to say when we are doing some like instead of 16 by 16 mesh, I am doing 256 by 256 mesh. I know which one is high fidelity. It's easy to know. And even if you go to models like, okay, I'm using RANS data for fluid flow as my low fidelity and DNS LES as my high fidelity. So but it's a much bigger issue, and I have not worked on it, but I have always assumed I have some expert opinion on how to rank them, and
same here. So I have
but
also
it's
done the
not going
same
to be
thing.
easy.
But
It's not
but
going
I
to be
wonder
easy
sometimes.
always.
Yeah. So yeah, I think that's all from my side. Thank you for this excellent talk. Very
No,
insightful. Actually.
If I could say one more thing,
Yeah.
so maybe we can do some um, model validation or selection kind of thing with the experimental data. If we have experimental data, then we can hopefully rank. That is one option, but costly option.
Very costly. Yeah.
Yeah.
Yeah. Rasul.
So I have a couple of questions. So I think one of the questions was maybe I'll start from backwards. So since you have this pruning of neural network, so there was this weighted L1, right?
Yeah.
And so I at one point I did see that the weighted L1 is basically, if I want to look at it, it's basically the weights are the inverse of the parameters mostly, but here you replace the parameters by the low fidelity parameters, right? Theta LF.
Yeah.
And theta is basically the parameters of your low fidelity parameter. I think that vector theta is basically the vector of low fidelity neural network parameters, right? Is it not?
No, this is during the high fidelity training. So I already trained my low fidelity version.
I see. Got it.
Identical network.
Mm-hmm.
And so essentially what both of these regularization, what they are doing is they're saying don't deviate too much from your low fidelity network parameters, because we have already fixed them by learning at least something about the problem. Right.
So my question was regarding this, that if you go this previous slide to this one, I believe. Here. I think the weighted L1 scheme, it seems that almost that if I have theta as the theta that you're showing here, not the theta LF, W times theta is almost like as if you are reducing it down to a vector of ones. Is it not?
Yeah.
Almost like a
Yeah.
vector of ones.
So yeah, again, it's trying to make sure you do not drastically increase or decrease your theta in an iteration. So drastically change your theta in one iteration. So that's how it's
I see.
regulating the training. So it's basically the theta that you are seeing, the two theta, one in the W and the other one in the theta vector, are essentially the difference is basically the two iterations, right?
I see. Okay.
Just to make sure you are you do not have only overemphasizing some of the connections. So do not make that jump. So that's what it is.
I was just trying to understand from the point of view that when I have just an L1 regulation over theta, I do understand that I'm trying to make the values of theta as small as possible. So the summation of all of those should kind of be as small as possible for L1 regulation. But when it is weighted sum, it's almost like whatever value any individual value of theta gets, I'm dividing by that value, right? And so basically the vector that I'm trying to kind of reduce, that value remains pretty much constant. So that's why I was kind of thinking like, so how would the weighted regulation? I can see the figure. That figure actually makes things much more clearer. But from just the mathematical formation, I was thinking like W times theta is almost like trying to create a vector of ones.
Yeah. So
no matter what the value of theta is.
Yeah, it's trying to say do not deviate too much.
Don't deviate from it. Okay, got it. I had another question, which was, I think, from the previous, the first question that Souvik asked. I think if you can go back, I think this was regarding the, yeah, this one, yeah, this slide, yes. So here, I think this is a very interesting thing that you raised, that you're training this low fidelity network and you're changing the parameters of this low fidelity network in such a way that that the step size is also being modified by the uncertainty, right?
Yes.
So you say that you will take a small step size in trying to learn a parameter if the uncertainty at that particular point is very high.
Yeah. That's what it says, right? You have e to the power minus, and then beta is a tunable parameter, by the way.
Right.
This is
so beta, I hope it's probably a positive parameter. Then this will be meaning that you're going to take a very small step, small learning step towards actually learning a parameter vector, which is related to that particular data point.
Yeah. So what is essentially saying, if the teacher is not confident enough, then whatever the low fidelity information is giving me is probably I have to rely on. But if the teacher is very confident, then I should believe the teacher.
So this sigma is a predictive uncertainty from the teacher.
Yes.
Okay, which means that if I replace it with some kind of a neural network, it has to be some kind of a Bayesian neural network or some kind of neural network that predicts uncertainty as well.
Yeah, I mean, there are a lot of things that you can do with teacher. Like you can replace it even with other networks. Like you were saying, if you want to replace with the Bayesian neural network, let's say, because ultimately that's what you want. All you want is that predictive uncertainty and mean prediction. So that's all you need to create the sub data set. Now you can do a lot of other things to essentially, if you use a standard network, then you can do a bunch of them, so that you will have those values as well, right?
Right. Just one last question, and this is just to again coming to the same point that when we usually update the parameters, we can use a stochastic variation inference, which typically uses just a single point to update. And then if you use a gradient descent, just a simple gradient descent, then it would actually kind of average across all the data points that you would have, right?
Yeah, so that's the thing. So what you are doing is modifying this eta for each individual one.
Each individual one. Okay, got
Yeah,
it. So you're basically using a stochastic variation inference.
So you can still do average. Then your eta will be, you have to use an average of the batch size you are taking. But in our example, we just did individual.
Okay, got it. Yeah.
Yeah.
Thank you so much. Any other questions from the students or anyone else?
I think we can wrap up now.
Yeah. Okay. If not, then yeah. Thank you so much, Dr. Shubhande, for this wonderful talk. It's very nice examples that you took. Really enlightening. Thank you so much for really being taking this time. I know that it's very early morning in you, and I know that you are not an early riser. But thank you again for this wonderful talk. So next week, I think we'll have Dr. Agnimitro Dasgupta for another talk on exciting talk on machine learning and their use in mechanics. So till then, thank you so much for joining in. We'll see you again next week. Thank you so much, Dr. Day.
Thank you for inviting me.
Yeah.
Bye.
Bye, everyone. Bye.